Okay, so this is a tutorial for EP228 Lab 3. Um, yeah, I'll just go through it question by question. I'll show you my code and kind of the nuances of it and how it all works, and hopefully it can help you guys. Yeah, so the plot that I have in front, I had to do some testing. I forgot a bracket in my code, but it's the plot of the drag coefficient b over m. And you can see the equation. It's both in your notes or in the assignment, and it's also just written out here in MATLAB. The key thing is to remember that v minus 35 happens before you divide it. That's what I forgot, and my function was very different. So it's standard to put it into your command window. Just set drag equals the model. That's the name of my function. And I've set my velocity to from 0 to 100 in steps of 0.1. And then we can plot our v versus drag. And that's when we get this plot. And this is what it's supposed to look like. So as you can see, as expected, the drag goes down as the ball goes faster, and that is due to the stitches on the ball. We'll get into what a smooth ball should look like in a few questions. So the first part is really, really basic. There's nothing to really worry about. It's just one graph. The next part that we have, though, is creating the Euler equations for the trajectory of a baseball. So we can start with, and lots of this is in our notes that Pasha posted, but we can start with the forces, and we have our gravitational force, our Magnus effect, and our drag force. These can be broken down where F net is ma, and remember that these are still vectors because we're assuming all directions x, y, and z. We're not assuming it's moving solely in the x or y direction or z direction. So we have ma, mg, F Magnus turns into b over mv vector. I didn't put the m in because we're assuming that b is just, that's our drag coefficient, what we coded just a little while ago there. This SO is also b over m if you look in your notes, but it doesn't matter, we're not going to be worried about it. Then we have this omega vector crossed with the v vector, and we will get into dissecting that in a second. So we can write out each of these vector forces into their components. We know that if you drew a free body diagram, you would find that gravity, of course, is acting down. Drag is acting 180 degrees in 180 degrees in the direction opposite of motion, and the velocity is just our velocity vector. So 0, negative g, 0, which makes sense, where g is just 9.81, the gravity constant. And v is vx, vy, vz. That should be pretty straightforward as it's just all its components. Then this omega v, we have to take the determinative because it is a cross product, and we get this whole equation. It's a fair amount of variables. From these, we can kind of piece together the basically, what would you call it? Our differential equations for motion, or for velocity rather. And that's just taking the x components, putting them together, the y components, putting them together, and the z components, putting them together. Nothing too crazy. Next, we're going to simplify though, and we can totally ignore the velocity in the z direction and the Magnus effect in the z direction. So anything that has that can be removed. So we get x equals this because we have vz here and omega z there. We are not concerned about them. So that whole term can be cancelled. Same with this, vz omega z can be cancelled. So these are what we're left with for our velocity differential equations. We can then create, and we can ignore the z direction, this whole thing completely, as we are not concerned about that direction at all. So our Euler equations can be derived by simply, well, basically you can take the derivative of this, the integral of this, and then again you get Vx from here, and then you could do it again and you'd get x. The main thing is to remember these delta t's. They're really important. If you forget those in your function, you won't get any graphs resembling what they should be. Yeah, so I think that's pretty straightforward now. This is in our notes, so if it's confusing, the more in-depth theories there. And but it's really just creating your differential equations and remembering that we are completely ignoring the z direction of motion. And from there you can derive these pretty quickly. So we have our MATLAB functions essentially, and we can start coding to get this plot. So we pull up the baseball function. We want our function to return a time array. It's not necessary, we don't use it in anything, but it is part of the requirements, so we will take it. But we have a time array, an x array, and a y array, and these are our x and y positions which we'll use to plot. We take in an initial velocity, an initial angle of being thrown, and our delta t. So this b here is just our drag coefficient, which we calculated in our model. We can just copy paste this over here. It's identical. To save space, I allotted g as 9.81, and remember to keep everything in meters per second. This is a counter so that my x and y and velocity and time can all be kept as arrays and be equal to each other. So at time 0, they all have that's the first column. So as you can see, our initial position in x is 0. Our initial position as allotted by the question is 3 feet, which is 0.9144 meters. And of course our first time interval is 0. I set v, for consistency's sake, in my while loop, which we'll get to, as v0, so that it just makes things a little easier. We can then set our vx component of v as cosine. This d in front of it means degrees. So you, instead of having to have a little bit of code in here that converts theta to radians, you can just use cos d or sine d, way easier, and I don't know, save some space. So same with the y, sine d theta times v, which is our v0 in this case. Now we use a while loop to calculate each step of our velocity and position. And we want to do it while y is greater than 0. As soon as y equals 0, we want it to stop, because that's when the ball hits the ground. So again, we have our drag coefficient. Since it's reliant on v, we have to keep reiterating it essentially. And v is not a vector; it is the magnitude of your final velocity, or your velocity at that step. So we have the next point in the array is equal to our previous point plus the velocity at that previous point times delta t. That the only thing for this is to remember your delta t and to remember that we need to use our previous values to calculate the next one. We do that, and we do it for the y again, remembering to use vy, not vx, and then we're done with position. Then we go into our velocities. It's again the previous velocity minus our drag coefficient, basically our Euler formulas. You can just put those in there. And remember that Vx, it's V magnitude times Vx if you're using the Vx, and V times Vy if you're using Vy. Then we can calculate our velocity at that point, and that's just the square root of the sum of the squares of our Vx and Vy. Boom, boom. Gives you V to use in the next equation. And we just increase our time, and yeah, and then we have our counter where we just increase it. So that is our function. And so if we want to use it, we can say set variable s, here, there we go, to baseball power hitter with an initial velocity of 110 miles per hour, which is, oh boy, 49.1744 meters per second. I'm sorry about the sniffling. I'm a little sick. And next we needed our theta, where we're just going to put it as 45 degrees. And finally our dt, which for this first one we'll use just 1. So now we have our oh shoot, you know what, I messed up. This should actually be txy, shouldn't it? Because it returns. Yes. So now that we have that array, if we want, we can plot x versus y. Those are our positions. And if we take a look, you can see that it's a somewhat parabolic curve. And since our time step is so large, it doesn't end right at 0 because it's going to calculate the next step. It's not 0 here, but it's way below 0 there, so it will of course include that point. If we want to hold that one, just by putting hold all, and we do this again with a 0.1 step, and then plot x and y again, you can see it's a much smoother curve, and it does end at almost 0. We can do one more, where it's 0.01, and plot that, and we get it where it ends pretty much at 0. And that's exactly what this plot looks like. So just remember to put your labels, x, y axis, and your title. And for each one of these, you might not want to use yellow as a color. It's kind of annoying. Yeah. Okay, now that we have that plot, we can it says be sure to test your code for different values of the time step. In general, is the trajectory of the parabolic. It is somewhat parabolic, as you can see here. I'll zoom in. It's somewhat parabolic, but because of the forces acting on it, it's parabola will be slightly cut short. So if we cut it here, you can see that there is a parabola, but it kind of gets damped. That's just because of the forces. Yes, there's a parabolic shape, but it is not exact. Okay. So you can see that just as I wrote, the shift away from the parabolic path is due to forces acting on the ball. So now we need to find the range of angles that correspond to a 350-foot hit, which is a home run. And I wrote a little function for it in a different window. We don't want to write it in our baseball power hitter. He doesn't need that for grading. He just wants to see that we got roughly the right angles. So my function is it takes in the initial velocity, the change in time. These you don't have to worry about. They're for those later questions. So we have a counter, and then we set theta to any angle, or increment angles of 0.01 from 0 to 90 degrees. And then we return these txy arrays again using our baseball power hitter. I put wind because you have to do this again, but it can just be baseball power hitter and v naught, theta, dt, v wind, h. Don't worry about the last two for now. So it's going to set this angle, and this is just an arbitrary word, array to the x end that shouldn't be there, but anyway, it'll set it to the last point in the array of x, which is our distance. And then it'll increase the counter and do that again. So if we run that, and set it just to a random variable, it does take a little while to run. It has to run through all those angles, right? It's calling a function, then running it. And then we can set our, or I guess we have our velocity and our x. So we can just set, an angle array from 0 in steps of 0.01 to 90. And now we can compare these. So if we double click on our x where it travels, you can see that it gives you its distance. And if we scroll through this until we find 350, which is right here, we can mark the column number 2061, go to our angle, and find 2061. And as we can see, that corresponds to a 20.6000 angle. You can do that again for your where it where it exits the 350-foot range, and it's the exact same process. So that'll give you your range. And I just gave an explanation of my method, and I will probably include my home run code. I don't think that should be in there actually. However, anyways, so on to the fourth question. So now we're going to assume that the ball is smooth. And all this means is that it doesn't depend, since there's no stitches, the ball's drag coefficient doesn't depend on velocity. It's going to meet the same amount of resistance no matter what. So it should be a linear, yeah, it should actually just be a constant. It'll be a straight line, no matter what the velocity. So, knowing that, when we go to code for a smooth ball, we can just set b over m to 0.009697, which, if you take the v out, is what it would equate to. And then you can plot for a rough and smooth ball. From my plot, you can see that the rough ball travels further, and the smooth ball doesn't travel near as far. It's about a 20-meter difference, give or take. This is because since there is turbulence around the baseball, the rough ball, it is easier for it to slip through the air, thus giving it so-called extra propulsion. It's not adding energy, but it's making the energy go further, be used more, and so it will travel further. The smooth ball, however, is not creating turbulence around it, so the drag will affect it and it will just fall. And to plot those, you just basically have to, you just have to take this v out. So you could put a 0 if you wanted, and then just go from there and plot it, and then be sure to put those v's back in because you're going to need them later. For the fifth question, it is asking us to include the effects of the wind. To do this, it may sound a little confusing because they give you this v equals the magnitude of v minus v wind as vectors. It's not actually that difficult. We can set before we had, zoom in here, before we had v just equal to the square root, or in the beginning we had it set to v naught. In the wind one, we are going to set v to be this square root of the sum of the squares, because we need to include v wind. So it'll be cos theta times v naught, because that's our x component, minus v wind, because we're just told that the wind is in the x plane. That's it. And then squared plus sine theta v naught squared for our y component. Our initial vx and vy vectors, though, are just cos theta, sine theta times v naught, respectively. We do not include the wind in the first one. Now we have v, that doesn't change, it's reliant on velocity. Our x doesn't change from the original function. The only thing that changes is that now we have, in our vx, we include v wind. So we have v times our magnitude of velocity times vxii, so our previous velocity, minus v wind. Remember, the vxii minus v wind has to be in brackets because they're isolated together. They are x vectors, they are not full magnitudes. Then multiplied by our time change. And it's exactly the same throughout. Ignore this b dot, that's for the next question. And then you just take the square root of the components, square root sum of the squares of the components, that stays the same. T, I all equal the same. So if we want to plot this, we can go txy, let's do wind. And let's say our wind is going 6 0.7056 meters per second, which I believe is a 15-mile-per-hour wind. And let's run that. We now can plot x and y. Plot x and y. And, oh, it didn't. Here we go. This is what our plot looks like with a headwind. If we put a negative value for our wind and then plot that, you can see it goes a lot shorter of a distance. And then if we completely take out the wind, it's right in the middle. So you can see that there's a bit of a spread of distance. This is with a tailwind. This is with a this is with no wind, and this is with a headwind. And remember, a tailwind is it's pushing the ball, and a headwind is it's pushing against the ball. Sometimes people get those mixed up. So that's all you really have to do for the next one. Remember, title, axes, plot labels, everything. And the maximum height of the trajectory is not the same in all cases. It varies very smallly. And I'll show you that here. It literally varies by like a meter. Not even, like 10 centimeters, I think it was. Yeah, you can see that there's slight variation. Yeah, if we zoom right in here. This is a little higher, you know, this one's kind of lower, this is in the middle. I didn't really worry about it, as it's literally a 0.01 of a meter, which is 10 centimeters, or 1 centimeter difference. So I wouldn't really worry about it. The baseball players are not going to be worried about that. Distance-wise, though, you should comment on that. The last part is just implementing the atmospheric pressure. And this is actually really straightforward. Okay, so in this function, it tells us that the new drag coefficient in the y direction, because that's where atmospheric pressure acts, is b times the exponential of negative y, which is your elevation, over h, which is just a constant of 7,000 meters or 7 kilometers. So I just set that h constant right here. B stays the same to start with. And then this is all the same. Then you get into your while loop, and I have this b dot variable. And b dot is just b prime. And it's your regular coefficient times the exponential of height or elevation over h. And then in your velocity, your position is unaffected because it relies on velocity. You can say instead of b times v times vyi, you can go b dot times v times vyi. And that is literally the only change. You'll have to change one line of code and put like 4 extra characters. And then when we run that, when we clear that, we can plot, we can call this basically and set a elevation of, say, 1,600, which is close to a mile, I do believe. Yeah, 1609.34. So let's do that. And if we do that and plot it and hold and then do this with 0, so sea level, and plot that, we will see, actually, I'm also going to make that one red. You can see that the ball in Denver goes further than the ball at sea level. And it's because the air gets thinner as you get higher, so there's less resistance. So closer to sea level, there's going to be a lot denser air, but as you get up into the atmosphere, so 1,600 meters is a fair amount of elevation, the ball is not going to experience as much drag, so it will go faster, or further rather, sorry. So that's all the parts that the question has. Yeah, it's not too bad, actually. If you guys have any questions, you can shoot me an email, which I will put in the description, I guess. I don't know. I'm going to try and make these available for other years too, because I do have friends going into EP. So I'm going to put it in the description anyway. If you guys need help, I guess you can use it. Yeah, I hope this was helpful, and I'm sorry it's a little jumpy. But yeah, cheers. Hope it works.